Hello and welcome to the first part of Chapter 1, Work and Energy. In this part, we focus mainly on work and its calculation. We're going to cover work for a constant force and work of some particular forces. First, starting with the definition, work of a force is the energy transferred due to the displacement of a body. Now, it's the energy transferred by the force or due to the force, or even it can be consumed as the body moves. However, it's very important to notice that work is transfer of energy or energy transferred, and it's not energy in the body itself. The body doesn't have work, the body does work. Mathematically, for a constant force, work is given as a scalar product of F, the force itself, dot AB, the displacement, or F times AB times cosine the angle in between. Work is expressed in joules, the force should be expressed in newtons, and the distance or displacement from A to B is expressed in meters. The equation that we've seen is the equation used for a constant force, and that's what we are supposed to know. However, if the force isn't constant, we have to go to a more complicated calculation, which is the integration. So we simply integrate the force dot dr, displacement, or to make things easier, we can say integral of f dot dr times cosine the angle in between f and dr, let's call it theta. Or better than using this, you can notice the equation written here in which we have used f the x times dx and fy times dy. This is inspired by the relation that we know in mathematics. And when we say u dot v as a scalar product, it equals x prime plus y prime. This makes things easier. Why is that? Because if you are dealing with a force on x-axis, you just use the x-axis component, and if you use the y-axis, you just focus on the y component. As an example, let's check this. The force done by elastic force. A body moves from O to a point at distance x from the origin or equilibrium position. Tension acts, or elastic force acts on the body against its motion. Tension, or the elastic force, is given by minus kx. Minus because tension or elastic force acts always against motion. The body is moving to the left, tension is going to be pulling to the right. Now, when we calculate that, the force is variable, so we have to use the integration. That is, in work of F equals integral of fx dx. Notice here we just use the x value because the force is only on x, which is integral of minus kx dx. Minus and k are constant, so they exit the integral, minus k integral of x dx. And we know that integral x dx is x squared over 2. From 0 to x, which is going to be minus kx squared over 2. Now, it's obvious that the work is negative. That's simply because the force acts against motion. It is a resistive force or a resistive work. In general, work of force elastic, when we move from x initial to x final, is nothing but minus half kx initial square minus half kx final square. Positive or negative determines whether the force is doing motive work or resistive work, respectively. Again, this is an additional topic. I talked a little bit about it. You will be using this next year, hopefully in university level, because problems are going to be a bit more complicated. You can get back to this whenever you want. Now, discussing or considering some particular forces, which we deal with on regular basis. These are the weight, the normal reaction, friction, tension, and elastic force. Tension and elastic force, we talked about them. We talked about elastic force in particular. Let's consider the others. The easiest is the normal. The work done by the normal reaction is always zero because normal is always perpendicular to motion. On the other hand, work done by friction is always given by minus F times AB. This is nothing but F times AB times cosine, the angle between F and AB, which is 180. This is 180, and we know that cosine 180 is minus 1. Hence, we get this equation, minus F times AB. We can directly use it without proving. Then, work done by weight, which is mg, Initial height minus final height, height A minus height B. We'll talk about how this equation was derived in a moment. Let's discuss this briefly. Again, we do not need to explain that in details when we are solving a problem. We just use the equation as it is. So work done by weight, let's say as you move from point A to point B, it equals, if we go back to the equation where we used x times x prime plus y times y prime, we get here, it becomes weight on x times delta x plus weight on y times delta y. To use this is 0 because weight has no component on x. If I just use this, you know that you need to have to assign a certain reference frame. Let's assume that upwards is the positive y. Then weight on y becomes minus mg, and delta y becomes y of b minus y of a. Now I'll move the negative sign inside, so I'll get mg ya minus yb. Since we took y to be vertically upward, this means that ya and yb are nothing but heights. So this becomes mg height a minus height b. This is one way of proving this equation. I could have used the basic definition mg times distance times cosine the angle in between, or anything else. This is one way of seeing it and proving it. Okay? In general, if we are considering motion on a path which is not straight, it can be inclined path, such as the following. We're moving from A to B along this curved path. Work of normal is always 0. Work of friction is minus F times AB. However, AB here isn't the direct distance. Let me use different color. It's not the direct distance from A to B. No, it should be the straight distance, the curved distance from A to B. So this AB here is the actual ground covered from A to B along the curved path. This is not something that we can calculate at the level of grade 11 or grade 12. This requires some advanced mathematics where we study functions in details. Okay, so this cannot be used if the path is arbitrary. It should be straight path or circular path so that we can calculate it using our regular tools. Work of weight in all cases is mg, height initial minus height final. So this is a very powerful equation, by the way. And it's remarkable that it depends only on initial height and final height. Initial and final. Now, what's the importance of this? If I do work, if I consider work, in fact, of a body moving from point A to a certain path, then moving back to point A, work done by weight from A and back to A is 0. This very simple idea is a notion of what we call conservative force. It's a force that does the same work in along a path from A to B. When it moves from B to A, it does the same work but with opposite sign. So altogether, work from A to B, then back to A, produces 0 work. This is what we call conservative force. Why conservative? Because such forces will contribute later to mechanical energy and cause no change to it. So these forces are referred to as conservative forces because they do not change mechanical energy. This is a fact that we'll be using later. For the time being, we just refer to it as conservative force as an extra vocabulary, nothing more. Now, an additional force, which is the radial force, this is highly used when we are studying circular motion. Let's say a body attached to a string and rotating, or a body moving on a circular path. There is always the normal reaction pointing inwards. Here, tension always points inwards. So whenever we have circular motion, it's important to understand radial force and its work. The work done by a radial force is nil, is 0. Why is that? The radial force always points inwards towards the center, while displacement is always on the circle itself. The radius and the circle are always perpendicular. They are always at right angles, as you can see in this animation. Thus, the angle between them is 90, and the scalar product between F and displacement is going to be 0. So this is a case that you can always use. Anytime we have radial force, remember this, in circular motion, the work done by that radial force is 0. Now, calculating for height, which is usually used in weight work calculation, you might have seen this in previous classes. However, let's go over this quickly, just as a recap. First, when motion is on an inclined plane, and we need to find height. Okay, so we have motion on a plane. Let's call this x, the distance covered actually on the plane. Height is the height of the point above a certain reference. To find height or relate height to the distance covered, we use trigonometry. Sine of theta, which is opposite over hypotenuse, is h, which is the height, over what? Over x, the hypotenuse. So h equals x times sine theta. Those who are watching this video and have official exams to sit for, I strongly recommend that you show this calculation in a figure anytime you use it. Okay? Sometimes it's simple, you don't need to do it. However, it's not wrong to show this on a figure, which makes things more clear. The second case is when we have a simple pendulum. Now, this might need a bit more work. Okay, to do this, let's go back to the figure, which is shown there. I'll call this point O. I'll call this lowest point B, this point A, and the projection here is going to be called H. Okay, the figure might be a bit messed up. So here it is something like this. This is B, the lowest point. This is A, the point I'm interested in calculating its height. And this is the reference where B is. The projection of A perpendicularly to OB is going to be called H. And this is what I'm interested in. The height of A is nothing but HB itself. Now, HB is OB minus OH. Now, the smart thing is coming to this triangle here, which I colored in green. And let's call this angle theta. In this triangle, cosine theta equals OH over OA. Now I can replace OH by what? By OA. So I have OB minus OA cosine theta. So we use trigonometry first, after using some geometry. Now, OB and OA, we know that this is a string attached to a mass. That string is always taut, so the length is the same. So instead of OB and OA, I can write L minus L cosine theta, and that's the height of point A, and voila, this is the relation you need to know. Now, the good thing is that we can use this equation directly in case the problem is straightforward. However, for some cases, you might be asked to show this relation. So I strongly recommend that you memorize it, to use it quickly and benefit of some time. But you need to know how to derive it, just in case you were asked to do. In case you were asked to derive it, show a figure and your calculation aside. In case you're not asked to do that, you can directly write it. I will leave that to you and your maturity to understand or evaluate whether you need to explain it or not.